Section 3.5, limits at infinity. Here we are concerned about the behavior of f of x as x approaches infinity. We want to determine what f of x tends towards as x approaches very large, positive infinity, or very small, negative infinity, in other words, large negative, values. The value y approaches is a horizontal asymptote. Now, this is often true, but not always. For your information, a function may cross a horizontal asymptote or a slant asymptote, but it can never cross a vertical asymptote. So our definition of a horizontal asymptote is the line y equals L is a horizontal asymptote of f if the limit as x goes to negative infinity is L, or the limit as x goes to positive infinity of our function is L. So a function can have at most two horizontal asymptotes. Why would this be true? Because of approaching both positive and negative infinity. So as x approaches infinity, the limit of f of x plus g of x is equal to the limit as x approaches infinity of f plus the limit as x approaches infinity on g. We have a similar rule for the limit as x approaches infinity on our product. Also, theorem, if r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r is 0. Let's think about this. Look at the limit as x approaches infinity of 5 over x to the 7th. As x approaches infinity, some number to the 7th power is going to be very, very, very big. Okay? So 5 over very, very, very big means we're going to 0. Now, BM, bad math. We don't really write this. That is bad math. Let's look at another example. Y equals 5 over x cubed. Let us recall, that's really 5 times x to the 0 over x cubed. We have our bigger exponent on bottom, so we have a horizontal asymptote at the line y equals 0. You may remember this from your pre-cal days. Bad math, 5 over x cubed, where the limit as x goes to infinity, 5 over infinity cubed, that's bad math, but we know that 5 over something really, really big is 0. How would we work with this one? Limit as x goes to infinity, 3 plus 2 over x cubed. We would divide this up if we go back to our basic limit rules. The limit as x goes to infinity of 3, which we know to be 3, plus the limit as x goes to infinity of 2 over x cubed is 0. So we get 3. So what this means is this function here is going to have a horizontal asymptote at the line y equals 3 because as x goes to infinity, y gets closer to the value of 3. Now, let's look at this example here. The limit as x goes to infinity of 4x plus 3 over x minus 2. We notice that as x goes to infinity, the numerator goes to infinity, the denominator goes to infinity, but this does not become infinity over infinity. This is not equal to 1. This does not work. So how do we do it? Well, we're going to look at the next page for the answer to this mystery. Divide the entire fraction. This means every term in the fraction by x to its highest power in the denominator. So if we look in the denominator, the highest power I have on x is x to the first. So we're going to divide every single term in the fraction by x and reduce. And notice that as x goes to infinity, this part goes to 0. This part goes to 0. The limit as x goes to infinity of the constant is the constant. And I get 4. Now, what did you notice about the limit and the function? Our limit is 4. Here's our function. You should notice something that you learned in pre-cal, and that is that the degree of the numerator and the denominator are the same, so our limit was the ratio of the leading coefficients, or 4 over 1. So, if the degree of the numerator and denominator are equal, then we have a horizontal asymptote at y equals a over b, where a is the coefficient of x in the numerator, b is the coefficient of x in the denominator. Our limit is the ratio of the leading coefficients. If the degree of the numerator is less than the degree of the denominator, in other words, bigger exponent on the bottom, the limit of our function is 0. In other words, we have a horizontal asymptote where y is 0. What happens if the degree of the numerator is greater than the degree of the denominator? Well, we do not have a horizontal asymptote. Okay, so that means we do not have this situation and we do not have this situation. What we know is our limit does not exist because the function is increasing if our function is going to positive infinity, or decreasing if our function is going to negative infinity without bound. So if the degree is bigger on top by 1 degree, you have a slant asymptote in the form of the line y equals mx plus b. So we're going to look at some more examples. So the last example dealt with the first property here. So let's look at this one here. Notice bigger exponent on bottom. So bigger exponent on bottom, the limit should be 0. That's what we think. Now we can check this by doing the process we did at the top of the page. Divide every single term in the fraction by the highest degree in the denominator, so by x squared. And what happens when I do this is I get 3 over x minus 1 over x squared over 2 plus 5 over x squared. And now as x goes to infinity, that goes to 0, that goes to 0, that goes to 0. We have 0 over 2, which is 0. So if we look at this one, this looks like our third property up there. So we think maybe the limit does not exist. So again, let's go through that same process just to check it. The biggest exponent on bottom is x squared. So dividing everything by x squared gives us this, 5x plus, as x goes to infinity, that goes to 0, that goes to 0, and I get my bad math, infinity over 2, which is still infinity. And remember how we write it. If our limit is positive infinity, we say our function is increasing without bound. If it's negative infinity, then we say our function decreases without bound. So what do you think happens if the limit as x goes to negative infinity on this function? What is happening? Well, I would have negative infinity over 2, so negative infinity. So we're going to negative infinity for my y values as x approaches negative infinity. Let's look at a couple of other examples. This is a good time to remind you once again about radii. Radii is a way to remember all the features you need to think about for graphing rational functions. R stands for roots, that's our x-intercepts, where y is 0. A stands for our vertical asymptotes, okay? Our function's not going to be defined there. T stands for two things, that's what the 2 is for. Tangency and togetherness. I write tango. In other words, an even power on our x minus c to the n in numerator will give tangency. In other words, we will bounce off of the x-axis for our root. And togo, togetherness, togo, what happens around the vertical asymptote stays around the vertical asymptote if we have an even power on that x minus c to the n. E stands for in behavior. This is what we've just learned. As x goes to positive or negative infinity, we have just now learned our 3 rules. If the exponents are equal, it's the ratio of the leading coefficients. If my exponent is bigger on bottom, it is y equals 0. And if my exponent is bigger on top, then we're going to have, if it's by 1 degree, a slant asymptote. All right, so let's look at this function here. F of x equals x minus 5 over x plus 2 times x minus 3. Now we can see our root is very easy. When x is 5, I will have a 0 for my y coordinate. What about my vertical asymptote? You can see that we have 2 when x is negative 2 and x is 3. We're going to write those as equations. What about t? Tangency and togetherness. Do I have a factor in the form of x minus c to an even power? I do not. So we do not have tangency. Do I have a factor in the form of x minus c to some even power in the denominator? We do not. So we do not have togetherness. What that means is around the vertical asymptote, If we are going towards negative infinity on one side, we're going towards positive infinity on the other as I approach that vertical asymptote. Notice that I have bigger exponent on bottom, because if you FOIL this out, you can see that this will be an x squared polynomial on bottom. So I have x to the first on top and x to the second on bottom, bigger exponent on bottom. So my end behavior is going to be a horizontal asymptote with the equation y equals 0. And y is my y-intercept, easiest thing when x is 0. So substitute a 0 everywhere, and we get a -5 on top over a -6 on bottom, which gives us 5/6. So we go and we graph the point 50, the point 056, and our two vertical asymptotes. And what we notice is, as x goes towards -2 from the left side, a number smaller than -2, that's going to be negative, that's going to be negative, that's going to be negative. I have a negative over a positive, which is negative. We're going towards negative infinity. Now pick, as we go to -2 from the right side, so bigger than -2. That's going to be negative. This is going to be negative. But bigger than -2, say -1.999, this is going to be positive. So I have a negative over a negative, which is actually positive. As we approach 3 from the left side, this will be negative. 3 from the left side, that is positive. This will be negative. So I have a negative over a negative, which is positive. And let's approach 3 from the right side, or bigger than 3. That's going to be negative. This will be positive. This will be positive, bigger than 3. So I have a negative over a positive, which is negative. And there's your graph. You have several examples you should look at, but let's look in particular at number 8 on page 204. And we want to think about what is happening as we go to positive and negative infinity. Well, first of all, you can see that this function is 2x times x minus 2. So that tells us about roots of the function. But I really want to look at some other things. I want to look at as we go to positive and negative infinity. Let's think about radii. From right here, if we factor this, we can see that I have roots when x is 0, when x is 2. I have a vertical asymptote when x is -1. No factor squared from this form, so no tangency. No factor squared in the denominator, so no togetherness. So what happens around the asymptote does not stay around the asymptote. We go in different directions. My end behavior, this is what we're going to be looking at. What happens as x goes to positive infinity and negative infinity. And the y-intercept when x is 0 gives me 0 over 1, which is 0. So this is the part that we have to actually look at. So I want to think about this in a couple of ways. All right, I want to go towards negative infinity and towards positive infinity. We're going to start with positive infinity. If we divide everything through by the highest agreed term from the denominator, we get this. Tells us that we have 2x minus 4 over 1 plus 1 over x when everything gets reduced. As we go to infinity, this term goes to infinity, this goes to 4, this goes to 1, this goes to 0. So as we approach positive infinity on our function, we're going to positive infinity. Well, what happens as we go to negative infinity? We're going to go through the same process. Everything gets okay here. But as we go to negative infinity, this is going to negative infinity. We still have 4 and 1 and 0. But notice that as we go towards negative infinity, on my function f, my y values are going towards negative infinity. So what we have is we actually are going to have something as x gets big, y is doing this. As x goes to negative infinity, y is doing this. We actually have what's called a slant asymptote. Y, the exponent on top, is bigger by 1 degree than the exponent on the bottom. Now, how can we find that slant asymptote? You learned how to do this in pre-cal. We take x plus 1, and that's what we're dividing by, and we're dividing it into 2x squared minus 4x. Now, I've got to add the plus 0 term, and let's think, what do I need to multiply x by to get 2x squared? 2x. So I'm going to distribute 2x across this. We get 2x squared plus 2x. Now, the whole reason for doing that was to get the 2x squared. So if we don't get 2x squared here, you kind of made a bad mistake. And here is my trick. Draw a line, change every sign, and add 2x squared plus negative 2x squared, 0. Negative 4x plus a negative 2x is negative 6x. Bring down the next term. Now, what do I need to multiply x by to get negative 6x? Well, negative 6. Distributing negative 6x across this gives me negative 6x minus 6. Draw a line, change every sign, and add. Negative 6 plus 6, 0. 0 plus 6 is 6. So this tells us that my slant asymptote is going to be y equals 2x minus 6 plus that remainder divided by what I was dividing by. Now, as x goes to infinity, what happens here? That goes to 0. So my slant asymptote is the line y equals 2x minus 6. And that is how we get our end behavior right here. Let's look at another way to think about doing this. What if we actually did synthetic division? We're dividing by a linear factor. What makes this 0 is negative 1. The coefficients of this polynomial here are 2 and negative 4. And negative 1 solves that, so that's what goes in our box. Bring the 2 down. Negative 1 times 2 is negative 2. Negative 4 plus negative 2 is negative 6. Negative 1 times negative 6 is positive 6, so we had to add a 0 for the linear term. 0 plus 6 is 6. Look at that. It's the same answer. It was sure a lot easier. I still get this. As x goes to infinity, we know that goes to 0. So my slant asymptote is the line 2x minus 6. Do you know there is a whole nother way to think about trying to get this slant asymptote or simplify this function? What if I did some creative math? My negative 4x could be written as positive 2x minus 6x. I'm going to write these two terms over x plus 1. Notice that I can factor out the 2x, and the x plus 1's cancel, and that is going to leave me 2x. Now what happens here? Minus 6x. And I can see that if I did 6x plus 6 minus 6, I could factor out the x plus 1 here. The x plus 1 is going to cancel. It's going to leave that 6, and this is what is left. And as x goes to infinity, this term's going to drop out. I'm still going to get this. Now here's what's neat about this problem. We knew we had a vertical asymptote at x equals negative 1. This slant asymptote is the line 2x minus 6. So I'm going to come down here, negative 6, up to over 1, up to over 1. My line is going to do this. What did I find out about my roots from above? My roots were at x equals 0 and x equals 2. Okay, I have a y-intercept at 0, 0. It didn't get drawn through it very well, but so here's my graph. And if I have no togetherness and I'm going to positive infinity as x goes to negative 1 on this side, then I have to go to negative infinity as x goes to negative 1 from the left side. And my function has to level out at this slant asymptote. So now you know more. Let's look at example number 4 from our textbook. F of x equals 3x minus 2 over the square root of 2x squared plus 1. How do we deal with that? Because I need x to go to both positive and negative infinity. And as we've seen before, they might be very different answers. So let's just go to positive infinity first, and then we'll go to negative. And notice that the largest exponent on x in the denominator is x squared, but it is under a square root sign. So in the denominator, we're going to divide by x squared. That's not a problem. What happens as I come out? Well, the square root of x squared, when x is positive, going to positive infinity, is x. So I'm going to divide in the numerator by x. In the denominator, we're staying under the radical, dividing by x squared. Remember that as x goes, if x is positive, the square root of x squared is x. Okay, so this would be 3x over the square root of x squared, and since x is positive, because we're going to positive infinity, the square root of x squared will be x. Probably see where I'm going with this. So simplifying everything, we get this. 3 minus 2 over x over the square root of 2 plus 1 over x squared. As x goes to infinity, this stays at 3, this becomes 0, this stays at 2, this becomes 0, this is under the radical, so I get 3 over the square root of 2 as x goes to positive infinity. Now let's see what happens as x goes to negative infinity. Remember that as x goes to negative infinity, if x is negative, the square root of that squared thing would be the negative answer. So, again, under the radical, that's not a problem, dividing by each term by x squared. But here, we're dividing by a negative x because x is going to negative infinity. That's going to give me the limit as x goes to a negative infinity. This is going to reduce to negative 3 plus 2 over x over the square root of 2 plus 1 over x squared. As x goes to negative infinity, we have negative 3 plus, still that's 0, over the square root of 2 plus 0. And we get negative square root of 3 over 2. So this is a case where we have two horizontal asymptotes. And here is a picture of that graph. As x is going to positive infinity, we're going to 3 over the square root of 2. Square root of 2 is about 1.4. So, and as we go to negative infinity, we are going to the negative of 3 over the square root of 2. Pretty cool. Your TPs for this section are number 1, A through F, that is a matching, 15, 17, and 27. See you next time.